Okay, I welcome you all for the problem solving session for the NPTEL course Fluid and Particle Mechanics. So we are in week 10 of the problem solving sessions, and the course instructors are Professor Sumesh P. Thampi and Professor Basavaraj M. Gurappa from the Department of Chemical Engineering IIT Madras, and the live sessions are handled by myself, Ankar Kartika, a research scholar from the Department of Chemical Engineering IIT Hyderabad. And the course code is NOC 25CH49. So as we all know, the course happens in such a way that theory sessions are handled by the professors, and we will be solving the problems in the um, during the problem solving sessions, which are conducted every week from Saturday 3 p.m. to 5 p.m. So, as we all know, this is a 12 weeks course and it is covering fluid and the particle mechanics. So, we are almost covering the syllabus in such a way that we have covered fluid mechanics as well as the particle mechanics. And in week 1, we have introduction to Navier-Stokes equations and their exact solutions for Poiseuille flow. And week 2, we have Taylor-Couette flow rheology, and week 3, dimensional analysis. Week 4, turbulent flow. Week 5, friction losses. Boundary layer theory, even though we haven't stick to the week wise course layout. We have covered all the topics mentioned above, apart from few which will be covered in the subsequent classes. So followed by introduction to particles, their characterization, particulate phenomena, motion of particles in a fluid, terminal velocity, particle separation, sedimentation of dilute, concentrated and flocculated dispersions, packed and fluidized beds, and filtration. So for books and references, we have Unit Operations of Chemical Engineering by Warren Lee McCabe, Julian Cleveland Smith, Peter Harriot, McGraw-Hill 2014. Fluid Mechanics by Frank M. White, McGraw-Hill. Introduction to Particle Technology, Martin J. Rhodes. And for few references, we have Coulson and Richardson's Chemical Engineering, John Metcalfe Coulson, John Francis Richardson, Butterworth Heinemann, Fluid Mechanics by Piyush K. Kundu, Principles of Colloid and Surface Chemistry by Paul C. Hemans and Raju Gopalan, Transport Phenomena by Bird, Stewart, and Lightfoot. So week 10 we have the course layout in such a way that we have effect of rough walls, roughness in turbulent pipe flow, pipes of non-circular cross section, and minor losses, sudden expansion and contraction, friction losses in sudden expansion. So yeah, we'll start with the problems now. So what we'll do is 60 500 60 40. Yeah, we'll see problems one by one, and yeah, we'll see the problems one by one. We'll see how to solve them. First one, a liquid of density 900 kg per meter cube and dynamic viscosity of 0.009 kg by meter second flows through a pipe made of cast iron. The pipe is 500-meter long and 200 in diameter. If the flow rate of the liquid through the pipe is given as 0.2 meter cube per second, then the average velocity of the fluid in the pipe is dash. So what I would like to do is I would like to give you guys 1 minute time, because all these are kind of familiar concept, except that we are kind of repeating it. So it should be easy to solve. So I'll give you guys 1 minute time. Please utilize that and solve the problems, and we'll discuss the answer Okay, so what we have to do is we know the flow rate and we know the pipe dimension, so we can calculate the a cross sectional area of the pipe, and from that we can calculate the velocity, because average velocity is equal to flow rate divided by the cross sectional area of the pipe. So by doing that we will get the answer. So yeah, I'll just come back. You use the formula and get the solution. I'll be back. So yeah, we'll now see how to solve the problem. So actually, what we have to do, we have to first calculate the cross-sectional area. So we'll go step by step. Liquid density is given as 900 kg per meter cube. Liquid viscosity is given as 0.009 kg by meter second. Material of pipe is given as cast iron, and length of pipe is given as 500 meter. Diameter of pipe is given as 0.2 meter, that is 200 mm, or in other words 0.2 meter. And what else? Flow rate is given as 0.2 meter cube per second. And what we need to find? We need to find the average velocity V. And as I mentioned, how are we going to solve? We are going to solve it by using the V is equal to Q by A. Here Q is the flow rate in meter cube per second, and A is the area, and V is the average velocity. And A, how will we find A? A is pi by 4 d square. So solution is A is equal to 3.14 by 4 into 0.2 square, because 0.2 meter is the diameter of the pipe. That gives us the cross sectional area. So here it is 0.24, 0.2 square is 0.04. So 0.04 by 4 is 0.01. 3.14 into 0.01, it gives us 0.0314 meter square. And V is Q by A. So Q here is 0.2 meter cube per second. So here 0.2 divided by 0.0314, and that will give us 6.37 meters per second. So V is 6.37 meters per second. I hope the question is clear and also the answer. So now we will go to next problem. Question 2. In question 2, what is given? The Reynolds number characterizing this flow is dash. So again, what we have to find? We have to find the Reynolds number. So again, it is a simple approach only. We all know how to calculate the Reynolds number. In today's class, what I am thinking is, I'll give you guys a minute time. So after that, we will discuss the solution, because most of the problems are kind of what we already saw in previous classes. So we can do that actually. Reynolds number is given by Re is equal to rho v d by mu. So using that formula, we can straight away get the Reynolds number of the problem. So we are going to do that only. So what are we going to find? We have to find the Reynolds number, that is Re. So Reynolds number is given for the pipe flow. We are talking about pipe flow. So Reynolds number in general is rho v into characteristic length by mu. So here the characteristic length is actually the pipe diameter. So it is Re is equal to rho v d by mu. So rho we know as 900 kg by meter cube. We calculated it in the last slide as 6.37 meter per second, and d it is point 2 meters, and mu is 0.009 kg by meter second. And now we are going to substitute everything in the Reynolds number formula, and what we are going to get is 900 into 6.37 into 0.2 divided by 0.009, and we will get Re as 127400. So that is the Reynolds number. And question 3 we have the roughness ratio is dash. And this is a new formula wherein I may give the formula epsilon by d, and epsilon here depends on the particle the material property of the pipe. And d is the diameter of the pipe. So based on these two parameters, we will calculate the roughness ratio. So with that note, I want to give you guys some time. Just epsilon you can find out from the material property. I think here the material is cast iron. So for cast iron, we have to see the roughness ratio, and we have to get epsilon for cast iron. So yeah, try to get it. In the meantime, I'll come. So we'll see how to solve the problem. And given pipe material is cast iron, and from standard tables the surface absolute roughness for the cast iron is approximately 0.00026 meters. And what we have to find? We have to find the roughness ratio. And formula, as I mentioned, it is epsilon by d, and epsilon here is 0.026 meters, 1.26 mm, and it is therefore 0.00026 meters. And roughness ratio therefore it is 0.00026 by zero point 0.2, that is 200 mm is the diameter, and we will get divided by zero point 0.2, we will get it as 0.0013. Roughness ratio is therefore 0.0013. Now so question 4, the friction factor can be calculated as dash. So here now we are asked to find the friction factor. So yeah, just see how to calculate the friction factor. I would say friction factor is dependent on Reynolds number. So whatever you calculate will be varying with respect to the Reynolds number, whether, and it depends on the regimes of flow, whether it is laminar or turbulent. So yeah, we'll see how to solve that. First, friction factor we have to find, and as we all know, before finding friction factor, let me just remind you of the Reynolds number. So we got the Reynolds number as 1,27,400. So on substituting the Reynolds number as 1,27,400, we know that the flow is turbulence and it is not laminar. So whatever the friction factor formula we are using, it should be suitable for the laminar. It should be suitable for the turbulent flow. So we're keeping that in mind, we'll see. So to find, we have to find the friction factor, and formula is F is equal to, yeah, as I mentioned, the formula varies depending on the Reynolds number. If Reynolds number is less than 2300, that is if it is a laminar flow, F is equal to 64 by Re. Or if Reynolds number is greater than 4000, we have this formula where it is 1 by square root of F is equal to minus 2 of into log of epsilon by 3.70 plus 2.51 by Re into square root of F. So this is Colebrook-White formula and it is implicit solved. And next we have F is equal to 0.25 by log 10 epsilon by 3.70 plus 5.74 by Reynolds number to the power of 0.9 to the whole square. This is a Swami-Jain formula and it is an explicit formula. Here we have f in both the left hand side and right hand side. That is why it is an implicit formula where we should solve it using iterative approach. Whereas in this formula we can directly use the formula and substitute it and get the solution. So that is the difference between these two. Now after knowing the correct formula, what we have to do, we have to just substitute it back in the since it is easy to use explicit approach, we are taking f is equal to 0.25 by log of epsilon by 3.7d plus 5.74 by Reynolds to the power of 0.9 to the whole square. And epsilon by d is 0.0013 as we calculated in the previous slide, where epsilon by d, what is it? It is the roughness ratio. So now we know epsilon by d as 0.0013 and we know the Reynolds number as 1,27,400 and everything else is known. So now what we are left with? We are left with just the direct substitution. We have to directly substitute it in the original formula and get the solution. So we'll do that. Log 10 to the log to the base of 10 epsilon by 3.7d plus 5.74 by re to the power re to the power of zero point 0.9 equal to log 10, and it is 0.0013 divided by 3.7 plus 5.74 by 1,27,400 to the power of 0.9. So now we'll calculate 0.0013 divided by 3.7 is equal to 0.00035, and this one divide plus 5.74 divided by 1,27,400 to the power of 0.9, and it will be 1.459 into 10 power minus 4 or 0.00015. Yes. This gives us 4.95 into 10 power minus 4. So taking log in this gives us minus 3.30. So this term alone gives us minus 3.30. Now if we substitute it here, what will happen? F is equal to 0.25 divided by minus 3.30 to the power of 2. So what happens? 3.30 to the power of 2 becomes 10.89, and 0.25 by 10.89, it gives us 0.023 or 0.0229, depending on the number of significant digits we can round it off. So our friction factor is 0.023. So that is how we do this particular problem. So the next one is So now we will go to next question. I hope question 4 was clear. In question 5, the head loss is obtained as dash meter. Now we have to find the head loss. And yeah, I'll give you guys 1 minute time. We'll see how to do that. Okay, we'll see how to calculate the head loss. To find head loss, and formula is that HF is equal to F into L into V square by 2 into D into G. Here F is the friction factor and L is the length of the pipe and V is the average velocity and D is the diameter of the pipe and G is the acceleration due to gravity. Solution is HF is equal to, now we know everything, so it is just a direct substitution. F is 0.023 into L. L is 500 meter. So we are putting directly as 500 into V square. V is 6.37 square divided by 2 is 2. D is 0.2. G is 9.81. So what we got? 3.924 in the denominator, and in the numerator we got 0.023 into 500 into 6.37. So it is 466.63 divided by 3.92. So that gives us 119.039 meters. So that is the head loss. And yeah, HF is 119.04 meters. So now moving on to question 6, what we have is okay, a similar question but change in numericals kind of a thing. So I request you to read the question first, and I'll give you 2 minutes because I want you to for calculate all the things. A liquid of density 800 kg per meter cube and dynamic viscosity of 0.008 kg by meter second flows through a pipe made of cast iron. Pipe is 600 meters long and 50 in diameter. If the flow rate of the liquid through the pipe is given as 0.15 meter cube per second, then dash. First is average velocity of the fluid in the pipe is dash meters per second. So yeah, similar question only. So I hope you got the answer now. V is again Q by A. So Q we know, A we have to calculate, and for calculating A we have the diameter. So it is a straightforward approach. So liquid density is 800 kg by meter cube, and liquid viscosity is 0.008 kg by meter second, and material of pipe is cast iron, and length of pipe is 600 meters. Diameter of pipe is 150 mm, or it is 0.15 meter, and flow rate is 0.05 meter cube per second. Okay, just a minute, I'll change few things in the question. 600.15 50 mm, it is okay, 150 mm. I changed. Yeah, 800.008. And what we have to find is the average velocity v. And formula is v is equal to q by a, and a is equal to pi by 4 d square, and solution, so a is equal to 3.14 by 4 into 0.15 square, which will give us 0.0176 meter square, and v is equal to q is 0.05 0.84 meter per second. I think I changed q actually. 0.05. Yeah, it is 0.05. So it is v is equal to 2.84 meters per second. So that is the value, that is the right answer for average velocity. So now what we'll do, we'll go to next question. Question 7, it is Reynolds number characterizing the flow is dash. So it is a very simple question only. So you can do it. So Re is equal to rho V d by mu. So to find Reynolds number Re, and formula is rho V d by mu. Solution is direct substitution. Reynolds number is equal to 800 into 2.84 into 0.15 by mu, that is 0.008. So it is Reynolds number is 800 into 2.84 into 0.15 divided by 0.008. So it is 42,600. Basically, it is turbulence flow. Why do we calculate Reynolds number? To identify whether the flow is laminar or turbulence, like what is the nature of flow. So for identifying that only, we calculate the Reynolds number. So in this particular question, Reynolds number came as 42,600, which is a quite high value. So considering that, what is the thing is, uh, it is a turbulent flow because it is greater than 4,000, and therefore it is a turbulence flow. So we will keep that in mind when we are solving further problems. So question 8 is again roughness ratio is dash. From the question, if we know, we can solve that it is made of cast iron. So material property remains the same. So we just need to calculate the roughness ratio. And for calculating roughness ratio, what we need, what is the formula? Roughness ratio is equal to epsilon by d. And we know what is epsilon and we know what is d. So by taking it, we can calculate the roughness ratio. I'll give you the pipe details. Pipe material is cast iron, and from standard tables, the absolute roughness for cast iron is approximately epsilon is equal to 0.26 mm, 0.00026 meters, and we need to find roughness ratio, and the formula is, as we know, it is roughness ratio is equal to epsilon by d. So solution is straight away simple. It is roughness ratio is equal to 0.00026 divided by 1.5, which is nothing but 0.00026 divided by 0.15, 0.00173. And moving to next question, it is the friction factor can be calculated as dash. And here again it is a similar problem to the previous problem, so which we can calculate very directly. Uh, so yeah, we just calculate it. We'll see how to do that in the next minute, because formula is the same as given in the previous question, so it won't be an issue. So we will see how to do. First, we have to find the friction factor F, and formula is again two based on the Reynolds number. One is like if uh, flow is laminar, we have RE is equal, F is equal to 64 by RE if Reynolds number is less than 2300, and if it is greater than 4000, we have that is in turbulent regime we have Colebrook-White formula, which is implicitly given as this 1 by root of square root of f is equal to minus 2 times log 10 epsilon by 3.70 plus 2.51 by re to the square root of f, and this is Colebrook-White implicit formula. And second one is Swami-Jain explicit formula, where it is f is equal to 0.25 divided by log of epsilon by 3.7d plus 5.74 by re to the power of 0.9, and this whole term has a square. So this is an implicit formula which requires iteration to perform the calculation and get the solution, whereas this is a straightforward approach wherein we can just substitute the numericals in the formula and get the solution. So we are going to use this formula for our solution. So we'll take this and write f is equal to 0.25 divided by log of epsilon by 3.70 plus 5.74 divided by re to the power of 0.9, and this whole term has the square. So now epsilon by d has 0.0017 because we calculated in the previous problem itself roughness ratio, which is actually was the ratio between 0.00026 divided by 0.15. So it is 0.00173, and RE is 42,600. So now we know epsilon by d as well as re, so we can directly substitute in this formula. So it becomes f is equal to 0.25 divided by log of 0.0017 by 3.7 plus 5.74 divided by 42,600 to the power of 0.9 to the whole square. So now first we'll evaluate this term. So it is log of epsilon by 3.70 plus 5.74 divided by re to the power of 0.9, and substituting it we have epsilon by d as 0.0017. So it is 0.0017 divided by 3.7 plus 5.74 divided by 42,600 to the power of 0.9. So now we have to evaluate these two. So 0.0017 divided by 3.7 gives us 0.000459 or 0.000046, and another term is 5.74 divided by 42,600 divided by to the power of 0.9. So it is 0.00039. So adding both will give us 0.00046 plus 0.00039 6 plus 39. It is like 0.00085, and taking log for that gives us 0.00085. Taking log gives us minus 3.07, and f now we have got the answer for this, like log 10 to the power of log 10 and log to the base of 10, and 0.00085 is minus 3.07, and f is equal to 0.25 divided by minus 3.07 the whole square. So minus 3.07 the whole square is 9.4249. Oh, it is wrong actually. 3.07 and square is 9.4249. And 0.25 divided by 9.4249 is 0.0265. So yeah, here alone small mistake happened. If you are finding anything during reading the PPT again, just let me know so I can change it from my end. So but yeah, answer is 0.0 5 to 5. So we are just taking 2 3 terms. So it is 0.0265. So this is the question 9 solution. So now moving to question 10, what we have is the head loss is obtained as dash meters. Now we have to find the solution for that. So again, similar to the last problem only, so we have to calculate the head loss, and we have the formula for head loss as HF is equal to FLV square by 2dg. So I'll give you 1 minute and we can discuss the answer later. So to find, we have to find the head loss, and formula is again, as I mentioned, it is FLV square by 2dg, which is a straightforward thing. So solution is again, we have to substitute everything in the formula. HF is equal to 0.0265 into length is 600. We'll just go back and check in the length is 600 meters. Head loss is obtained as dash meter, so it is head loss, and formula we know, and point F we calculated as 0.0265 into 600 into V is 2.84 divided by 2 into 0.15 into 9.81. So 0.15 is meter diameter of the pipe, and G is 9.81 and 2 is 2. So 0.0265 into 600 into 2.84, and calculating that we will get 0.0265 into 600 into 2.84, that is 128.24 divided by 2 into 0.15 into 9.81, so that is 2.943. So 128.24 divided by 2.943 gives us 43.57 or 58 meter. So that is the answer. Head loss is given as 43.58 meters. So yeah, okay, we will take a small break at this point. So yeah, we'll take a small break and we will continue actually. Time is 3:55. We'll come back by 4. Okay, we'll start now. So yeah, in all these it is in head loss is in meters. So I hope that is clear. Okay, moving on to question 11, what we have is the pressure drop across the pipe is dash kilopascals. Again, the thing to be noted in this is we are asked to give the answer in kilopascal, and for that what we need to do is first we have to find a pressure drop across the pipe in formula. So first let us see what the formula is. First, we need to find pressure drop across the pipe, and it is delta P, and formula is delta P is equal to rho G HF. So here we know rho, here we know G, and here we know HF, which we calculated in the last problem. So solution is similar. So 800 into 9.81, 800 kg by meter cube into 9.81 into 43.58 equal to I'll do the calculation again. 3 okay 800 into 9.81 into 43.58. So it is 342,015.84 Pascal, or it is 342.01502 kilopascals. So it is in pascals, and in the question it was explicitly asked to calculate it in the kilopascal. So it is 342.02 kilopascals. So that is for question 11. So now we have one more problem wherein we are asked to find the hydraulic diameter of the channel shown in the following figure. The hydraulic diameter of channel shown in the following figure is dash micrometers. So what is given? We have a channel where fluid is passing in from one inlet and flowing out through the other inlet, and we have a height of the entrance is 30 micrometers, and width W is 20 micrometers, and length is 80 micrometers. It is in micrometers actually. 80 not micro, yeah, 80 micrometers only, let it be. So now what we have to do, we have to find the hydraulic diameter of the channel. So why are we going with the hydraulic diameter of this channel? Like normally if it is a pipe flow, what we do, we take the diameter of the pipe. But in the hydraulic diameter, I mean, when the pipe is not having a circular cross section, we use the term called hydraulic diameter. So it is used in the fluid mechanics, where it defines the effective diameter of a circular pipe for a non-circular flow channel. And mostly it is defined as hydraulic diameter is equal to 4 times the cross-sectional area of the flow and divided by the perimeter of the wetted channel. So when we calculate this hydraulic diameter, we can use the circular flow principles to be applied to non-circular ducts and channels. So we are calculating the hydraulic diameter. This diameter we can use it to calculate the Reynolds number. So normally in pipe flow we use rho v d by mu, but in rectangular channel flow we don't know what is d. So in these cases we can calculate the hydraulic diameter and use them. So that is the case. So hydraulic, okay. into cross-sectional area by wetted perimeter, and here what is the cross-sectional area? It is comprised of h and width. So h is 30 microns and width is 20 microns. So what we are going to do, h is 30 microns, width is 20 microns. So these are the given things. Now find the hydraulic diameter. We need to find the cross-sectional area. So cross-sectional area is A into B for this rectangular thing, divided by wetted perimeter, and that is 2 times a plus b, 2 times of a plus b. So it is 4 into a b by 2 times of a plus b. Okay. Instead of ab I'll put hw, that makes sense. 4 into h is 30 and w is 20, divided by 2 times of 30 plus 20. So that gives us the wetted perimeter. I mean this is the wetted perimeter, this is the cross sectional area into 4. So 4 into 30 into 20 divided by 2 times of 50. So that gives us 24 and 24 micrometer. So what does this mean? It is our rectangular cross sectional area has 30 micrometers and 20 micrometers in the height and the width direction respectively. But here the hydraulic diameter of the channel gives the values in between these two. It is kind of like a flow characteristic length it is calculating, so we can take it in that way. Hydraulic diameter is actually given by 4 times the cross sectional area divided by the wetted perimeter. So that is the question 12. Now yeah, we'll go to question 13. In question 13 it is given that pressure drop in a 600 mm diameter horizontal pipe is 200 kilopascal over a length of 100 meters. The shear stress at the pipe wall is dash kilopascal. So yeah, solution, I'll give you the answer. First we'll see how to do, later we will discuss. What is given? We are known the pipe diameter is 600 mm and pressure drop is 200 kilopascal and pipe length is 100 meters. And yeah, what we have to find? We have to find the shear stress at the pipe wall. So what we'll do? Just give me a minute. Okay. Shear stress at the pipe wall. So now what we are going to do? Okay. So first we have to find the formula. Tau W is equal to delta P into D divided by 4 times of L, and therefore it is just a direct substitution, so during which we will get the answer. So tau W is equal to 200 kilopascal, so it is 200,000 into D is zero point 0.6 and divided by 4 into L is 100. So if we want, we can go back and check in the formula. Sorry, in this given, L is 100 meters, D is 0 point 0.6 meter, and pressure drop is 200 kilopascal. So that is what is given here. So we need to calculate it actually. We'll do it once again. Into 0 point 0.6 divided by 4 divided by 100. So it is 300. Oh, it is not kilopascal. It is pascal and it is 0.3 kilopascal. Sorry, it is 300 pascal divided by 0.3 kilopascal. So next question is, what is the pipe head loss in meters? Note that the pipe head loss includes the change in pressure head and gravity head. So we have a pipe head loss in meters, and we have to note that pipe head loss includes the change in pressure head and gravity head. So here we have a mercury and we have some globe valve where flow is from this to this, and we have the distances 3 meter, and we have 20 centimeter manometer reading. So now we have to calculate the pipe head loss. So we'll go directly to the solution. So what is given? It is given that is it 20? Yeah, it is 20 centimeter. So it is mercury height difference is 0 0.2 meters, and formula is simple, like total loss is equal to mercury head loss into rho water by rho mercury minus 1. So here it is rho water is 1000 kg per meter cube, rho mercury is 13,500 kg per meter cube. Okay, I think I did wrong. Minus 1, 13,500 divided by 1000 minus 1 into 0.2. So actually it is like this one is messed up. So that is the answer actually. It is 2.5 meters. Oh. That is for question 14. Now we will go to question 15. In question 15, what we got? Consider the figure given below. There are 125 feet of 4-inch pipe, 75 feet of 6-inch pipe, and 150 feet of 8-inch pipe, all cast iron. There are three 90-degree elbows, one, two, and yeah, and an open globe valve, all flanged. If the exit elevation is 0 and the operating fluid is water at a volumetric flow rate of 0.2 feet cube per second at 20 degrees Celsius, then dash. So what is given? We have to consider the figure given. We have 125 feet of 4-inch pipe and 75 feet of 6-inch pipe and 148 feet of 8-inch pipe. All are made of cast iron, and we have the water flow rate as 0.2 feet cube per second, and we have to calculate certain things. This is the problem statement and this is the associated figure. Now coming to question 15, what we have is the roughness ratio in the 4-inch pipe is dash. So the first pipe is the 4-inch pipe. If you go there, this is a 4-inch pipe, and for calculating the roughness ratio, what we have to do is we have to calculate the epsilon by d, and d here is pipe diameter, epsilon here is the roughness height or absolute roughness, which is for cast iron it is 0.00085 feet, or it is 0.00085 into 0.3048 meters. So it becomes 0.00085 into 0.3048, 0.00026 meters, and pipe diameter is 4-inch, and it is 4 into 2.54. I am using everything in SI unit. If anything required, we'll calculate at the end in respective units. So it is 0.1016 meters, and what we have to find? We have to find the roughness ratio, and formula is roughness ratio is equal to epsilon by d, as we have seen in the previous thing only. So now we know epsilon and we know d, so we can easily calculate the roughness ratio. So it is 0.00026 divided by 0.1016. So it is 2.559 into 10 power minus 3, 0.00256. So roughness ratio is 0.00026 divided by 0.1016. Okay, so it is 0.0026 that is the roughness ratio. And question 16 will go, the roughness ratio in the 8-inch pipe is dash. So last time we calculated for 4-inch pipe, and this time we are going to calculate for the 8-inch pipe. And it is, roughness height is again the same because it is made of, all are made of same material. So roughness height is 0.00085 feet, and it is in meters, it is 0.00085 into 0.3048, and it is 2.59 into 10 power minus 5, sorry, minus 4. So it is 0.00026 meters. And pipe diameter is 8 inch, so it is 8 into 2.54 into 10 power minus 2. So it is 0.2032 meters. And what we have to find? We have to find the roughness ratio. And formula is, roughness ratio is equal to epsilon by d. Epsilon is 0.00026 divided by 0.2032. So that gives us the value of roughness ratio as 0.001279, or yeah, 0.0013. So roughness ratio here is 0.0013. Similar way we can calculate the roughness ratio for 6-inch pipe also, but I think we haven't done that. But the procedure remains the same. So for example, if it is a 6-inch pipe, what will happen? Diameter will change. So it is 6 into 2.54 into 10 power minus 2, 0.1524. So it is 0.00026 divided by 0.1524, and that gives us 1.7060 into 10 power minus 3. Yeah, for 6-inch pipe. So depending on the diameter, here it varies because roughness height is same as it is a material property. Now going to question 17, what we have is, the flow rate through 4-inch pipe in feet cube per second is dash. So flow rate is actually given in the question itself. It was some 0.2 feet cube per second. Yeah, it is a straightforward question because we are not asked anything. In the question itself, it was given that flow rate is 0.2 feet cube per second. So yeah, it is 0.2 feet cube per second. So now next question is how to calculate the average velocity of the fluid through the 4-inch pipe, and it is asked in feet per second. So as we know, actually we have to convert one unit actually. So given it is 0.2 feet cube per second, and inch to feet also we can do. 1 inch is 4 into 2.54 into 10 power minus 2 divided by 0.3012. So it is 1 feet is equal to 0.30. Just a minute, I have a doubt in the conversion actually. Inch to feet. inches. Yeah, it is wrong actually. That's what I was thinking. It is 0.3333. 0.3333. So it is 0.3333 feet. 4 inches 0.3333 feet. And average velocity, how will we calculate? We'll calculate it using V is equal to Q by A, and Q is 0 0.2 feet cube per second, and A we need to calculate. So it is, we can actually calculate A separately, I guess, because it went wrong now. A is equal to, insert equation symbol, pi by 4 into d square. 3.14 divided by 4 into d is 0.3333 square, and that is equal to 3.14 divided by 4 into 0.3333 square. It is 0.0872 feet square, and it is 0.2, then everything else comes wrong, 0.0872. That is equal to 0.2 divided by 0.0872. 2.29 actually, not this much. 2.29 feet per second. So what we did is, we are asked to give the average velocity in feet per second only. So for that, to maintain the feet per second, we calculated everything to feet. So Q is 0.2 feet cube per second, D is 4 inch. So 4 inch, 1 inch, we just convert inch to feet, and find is average velocity, and A is pi by 4d square, and after finding out A, we can get the value of average velocity V. V is equal to Q by A, so we can directly put it. So actually, if 0.1 inch is equal to 4 into 0.0833 feet, just for the conversion factor. So V is equal to Q by A. Q is 0.2, A is 0.0872 feet square, and equal to 2.29 feet per second. So that is question 18. And now we'll go to question 19. Okay, I think we need to change, so we'll let it be. Reynolds number for the flow in the 4-inch pipe is dash. So we have to find the Reynolds number. So it is, okay, I messed up here. 2.29. 2.29. So Reynolds number is Re, and density is 1000 kg per meter cube, and V is 2.29 feet per second. So feet into meter, again it is 1 feet is equal to 0.3048 meter. So it is foot to meter. 1 is 1 foot is equal to 0.3048. So it is 2.29 into 0.3048 is meter per second. That is equal to 0.6980. Not meter per we can use it in meter per second actually. In the question, actually what is given is how we got rho as operating fluid is water, so that's why rho is 1000 kg per meter cube. I'll mention that maybe here. uh, Fluid density rho is equal to water, and velocity we calculated. Diameter is 4 inch. 4 inch again it is 4 into 1 inch, 2.54 into 10 power minus 2, 0.1016 meters. So now we can calculate Reynolds number, which is nothing but rho is 1000 into V is 2.8 and oh, not 2.8, V is actually 0.698, 0.6980, 1000 into 0.6980 into 0.1016 divided by 0.001. So answer is actually 70,916.8. So there was some calculation error. And fluid viscosity also I should have mentioned. Mu is 0.001, 1 kg by meter second. So yeah, everything else is direct substitution only. I think it should come next. It is given, and this is to find Reynolds number, and yeah, solution we can do directly. So that is for question 9, and we have a last problem. The friction factor in the 4-inch pipe is dash. So yeah, we have to calculate the friction factor in the 4-inch pipe. So how do we do? I mean, it is like similar to the last problem actually, nothing new over here. So it is to calculate the friction factor, and F is equal to 64 by RE if laminar flow, and if RE is greater than 1000, that is as in turbulent flow. So we have 1 by square root of F is equal to minus of 2 times of log 10 in of epsilon by 3.70 plus 2.51 by RE to the square root of F. Okay, this is implicit formula, and this is Swami Jain explicit formula, which we used in previous thing also. So we'll directly go there. So what is the material? Yeah, roughness is 0.00800026 meter. So we can use that in our formula. Actually, this is the original thing. The friction factor in the 4-inch pipe is dash. And friction factor F, I mean, we use the formula. Now we have to just substitute it. So epsilon is 0.00026 meter, and D is 4 inch, which is 4 inch 2. 0.1016 meter. Epsilon by d is 0.00026 divided by answer. It is 0.00256 or 0026. And now we have to calculate it. Log of epsilon by log of epsilon by 3.7 d plus 5.74 divided by re to the power of 0.9. So it is 0.00256 divided by 3.7 plus 5.74 divided by, actually our Reynolds number changed in this, 70,916.8. Maybe we can write it here. RE is equal to so it is now it is 70,916.8. 5.74 divided by 70,916.8 to the power of 0.9 is actually 0.00024. This is not this big actually. 0247 and 0.00256 divided by 3.7 is 0.00069. So adding both, what will we get? 0.00069 plus 0.000247. It is 9.37 into 10 power minus 4, that is 0.000937. Minus 3.02. Like here it is minus 3.02. So now here we have to substitute it in the original formula. So F becomes 0.25 divided by 3.02 square, 0.0274. Oh, okay. Yeah. 3.02 square is actually 9.1204. 9.1204. 0.25 divided by 9.1204. So it is 0.0274. So that is how we calculate the friction factor. Actually, in the assignment problems, there are similar problems to this with various number change. So I haven't included those problems, but one problem in continuation to this is there are a few cases were discussed in the assignment problem, wherein you have to submit about turbine and yeah, I'll just see that question once. It is like about a turbine head loss, turbine head in feet per second. So what at that time you have to do is you have to just add all the head coming from this and sum it up and put it there. So that is how we do that problem. So actually, like first we have to calculate for individual pipes, like 4-inch pipe, 6-inch pipe and 8-inch pipe. So first we calculate F. From F we calculate the head, similar to how we did in the previous problem. So after calculating those, we calculate for the elbows and valves and all. So after that we add it everything together. That will give the kind of give the turbine head. That is one of the questions extended, and rest are all three questions which were given, like loss coefficient for sudden expansion, for 90-degree elbow, for entrance. All those questions are like kind of you know the answer. So if you just think, you can answer the questions actually. So apart from that, there are many questions in this week's assignment, but yeah, everything is one point. So you should be like aware of the concepts much more than the problems, because problems are very simple in this week, like wherein you have to calculate the average velocity, and from average velocity you can calculate the Reynolds number. So from Reynolds number you can determine which friction factor model to use and determine the friction factor, and after friction factor we can calculate the head loss in the system. So this is the basic sequences which we followed. So if we go and see that question 6, we will understand better. So first we found the average velocity, and next we found the Reynolds number, and Reynolds number we calculated the roughness ratio because in the friction factor calculation we would require the roughness ratio. So after finding the roughness ratio, we use the friction factor formula and got the solution for the thing. So after finding friction factor, what did we do? We calculated for the head loss. So head loss is obtained as dash. So it is FLV square by 2dg, where F is this thing and LV square by 2dg. F is friction factor calculated in the previous problem, and L is the pipe length, V is the velocity which we calculated, and 2dg, d is the diameter of the pipe. So these are all the common things which will, like kind of chances of it going there, going wrong might be there, because everything is numericals. So make sure you are giving the desired answer in the correct units, because in some places it is in feet, some places it is in meters, some is in inches. So whichever you are following, use one thing fully, and then in the question, I mean in the answer, whatever unit it is being asked to give, use that. Okay, so that is one suggestion. And we did mostly that. Hydraulic diameter we studied, which we use when we are having with the non-circular cross-sectional flow pipes and all. So shear stress we saw, and yeah, this is the roughness ratio. Mostly the problems are simple. We are left with only theoretical questions. I hope you will be able to answer it based on the assignment, sorry, based on the lecture given by the professors. So if there are anything else we can discuss, or else actually I am done with today's session. Like we discussed 20 problems. So yeah. That's it for today's session. If we have anything to discuss, we can discuss, or else we can, close the session. Um, So yeah, if nothing is there, I'll close the session. Thank you for attending today's session. We'll meet again next week at the same time, 3 p.m. to 5 p.m. Yeah. Thank you for once again for attending today's session. Yeah. If there are any doubts, let me know. We'll can talk or else we can close it. Yeah. I'm closing the recording first. Or yeah.